Hello and welcome to the demonstration of Cluster Insight, a tool for exploring large textual data using clustering. This application is based on a weighted clustering algorithm that we have coded and encapsulated in a Python package. Finally, we developed an easy-to-use web application containing a pipeline for the analysis and exploration of large textual data. Our proposed algorithm is based on Lasso weighted k-means, or LWK, which is a powerful weighted clustering algorithm that preserved the simplicity and computational efficiency of k-means. So we adapted LWK to textual data, which gave very good clustering results. Then we took advantage of the feature weights to perform cluster exploration, which is one of the most challenging topics in clustering. And finally, we integrated this algorithm into a web application and proposed an integration with generative models as post-processing step to help us interpret clusters. The entire solution is Dockerized, so the application can be implemented locally or for internal usage with no installation required. The repository that we published contains a usage example of clustering algorithm that allows to import and process textual data, perform and evaluate clustering quality, and finally explore the results. And here is a simple example of usage. The Cluster Insight application is fully and easily customizable through a Jupyter notebook that we will publish soon. Now let's move to the demonstration of Cluster Insight. The application interface looks like this. We begin by setting parameters, starting with the choice of data, where we have proposed two types of import. First, a set of preloaded benchmark datasets, such as BBC News, 20 news groups, etc. And after selecting the dataset, a quick summary is shown below based on the original dataset labels. We indicate the recommended number of clusters and the corresponding labels. Otherwise, we have the possibility to fetch documents from PubMed using API calls. You can use it by entering keywords, and the application automatically fetches the chosen number of documents containing the keywords. Then it stores and tokenizes them locally. After selecting the dataset, we choose the number of clusters and then the number of top terms that will be displayed for cluster interpretation. After starting clustering, the application processes data, then performs clustering. Once clustering finished, a global clustering summary is displayed, starting with a recap of the number of documents, vocabulary size, and clustering results by comparing the predicted labels versus true ones, if we use the benchmark datasets. Then we plot the proportions of documents and terms per cluster, a word cloud to have a global ID on the topics, and finally, the 10 most important features that have been extracted by the clustering algorithm, which in fact corresponds to the document's terms. After showing the summary, we move to the exploration of the clustering results. Each cluster is shown in a different box and contains a word cloud and the most significant terms extracted from each cluster. Let's take a look on the first cluster. The word cloud is based on terms frequencies of the documents contained within each cluster. This helps identifying key features and many details of each cluster. Then we show two sets of terms. The first one is based on frequencies of the terms, which we call general insight terms. It's a well-known method used to explore general topics of clustering. So if we look at the general insight terms, we can quickly detect the cluster topic since these terms are often too frequent within the clusters. For example, in the first cluster, the general insight terms are hepatitis and HAV for hepatitis A virus, which indicates that this cluster is most likely associated with hepatitis A disease. The second set of top terms is called specific insight terms. This time, terms are based on the weights extracted by the clustering algorithm. Since these terms are the most important ones for the separation of clusters, they help identifying the key topics within clusters, and thus highly specific to their cluster. If we take a look at another cluster, the third one for example, which most likely corresponds to hay fever based on the general insight terms, we see that the second set of terms are very specific to the cluster, like iotaxin, which is one of the most commonly observed protein, as well as causes and medications for certain seasonal allergies, etc. So, the joint analysis of these two sets of top terms is interesting, since general insight terms provide a broad overview of the topics, while specific insight terms show the detailed topics that are covered. And the more terms we explore, the further we dive into topics contained in the cluster. However, since the analysis and interpretation of these terms can sometimes be challenging and too specific to certain topics, especially in medical context, we proposed using a generative model as a post-processing step to help us in exploring these top terms. To achieve this, we added the button to copy all top terms with a preloaded prompt and ask, for example, ChatGPT to interpret them using, for example, only 100 term limit. So let's do this using ChatGPT. So we see that the analysis returned by the generative model is very interesting, since it gives a good explanation of the cluster by connecting the top terms on one hand and by explaining each word within the cluster context, especially acronyms. And since we are dealing with an unsupervised task, this could be very useful for exploring the clustering of large textual corpora without requiring a lot of computing resources or fine-tuning. So this brings us to the end of the demonstration. Thank you for your attention.